Thank you, and welcome to part 2 of 4 of our corporate affiliate series with the RAIC. Today's webinar is Daylight from Above, Technical Considerations.
So my name is Monica Bulos. I presented the first part. So if you attended last week, I was the one presenting on daylight strategies. I am the architectural project coordinator with Velux. I graduated from Carleton University 2 years ago from Bachelor of Architecture. So I do have an architecture background and then joined Velux shortly after. And from that, learned a lot about daylight and design, which is a lot of what we are presenting in this series. And today, Russell is going to be presenting the bulk of this presentation in regards to technical considerations.
Thank you, Monica. As Monica said, my name is Russell Ibbotson. I'm the technical manager at Velux Skylights. And Monica did something fun last week. She took us through a couple of slides that led us to where she is today and demonstrated her passion for the subject. So I thought I would give it a try and do something similar. So 18 years ago, when I got out of school as an engineer, I was working designing solar water heaters. And I studied the physics of the sun's path and really studied on how to optimize the energy capture for thermal purposes from the sun. So energy is really my starting point in solar. And then about halfway through my career, I transitioned to being interested in passive solar design, getting more involved with buildings and the high performance buildings, different programs that builders and architects were using. And I joined Velux just under 10 years ago. And when I joined Velux, I realized quite easily from when you see some of our marketing pictures how beautiful daylight can be in a building. And I was introduced to different ways to design with daylight. That daylight was measurable, that you could use a lot of the techniques and principles that Monica spoke about last week in order to achieve beautiful design with daylight. Um, at the same time, when I joined Velux, I started looking into Active House. Velux was one of the founding members of the Active House Association, or Alliance, sorry, in Europe. And this is a high performance building program. It does a bunch of things with energy and comfort and environment. And for my sake today and for my general interest, it does a nice job of trying to give you the tools to balance the need to have high energy, high performance on the energy, but also giving you the consideration on how to get the high performance on your daylighting design. So that leads us into today's presentation. Velux is a family-owned business. We've been around for nearly 80 years now. Next year it'll be 80 years. And it's still the original family that owns it. It's headquartered just north of Copenhagen in Denmark. We have offices in 40 countries, and we've been in Canada for over 40 years. We do very well selling skylights around the world, and most of the profits that we have get distributed through 4 foundations that the owners operate, and they do this through grants for research and for education and for culture. I guess it's a bit of a Danish thing to give back to the community like this. We also host such events as the Daylight Symposium, Healthy Buildings Day, and the International Velux Award for Students. So we do quite a bit within the architectural community around the world. Now the name comes from ventilation and lux, the Latin word for light. And the founder of the company really had it in mind that he wanted to bring both daylight and fresh air through the roof. And I have to say, that's become my goal as well, and part of what we're going to try to inspire you with this 4-part series that we have going with the RAIC. So I better start my presentation. We've got, sorry, I'm going to do a quick recap from last week first. So Monica was our presenter last week, and she presented on Daylight from Above, design strategies. And she really broke this down into 3 principles, and she demonstrated these using computer models, physical models, and actual case studies. So this image here is showing a luminance. So and this is a computer image that's giving you the first principle, which is that daylight is more powerful from above. So you're going to get more daylight through skylights than from vertical windows. And this is in plan view, the same building, and this is showing daylight factor. So you can get an idea that you're getting a more even distribution of light, a deeper spread of light through the space, so that skylights can provide a really nice quality of light and amount of light. And then the second principle was looking at the scale and the positioning of the skylights, and how moving the skylights around on the roof and the ceiling can create different effects in the light. And one of the things we like to talk about is that you don't see daylight until it hits a surface. So when you're bringing in daylight from the roof, you can determine where you want that light to land in order to create the effect with the lighting that you're looking for. And the third principle was really looking at the ceiling design and how to optimize the lighting performance by both minimizing the horizontal ceiling and increasing the light through design. So this one's really interesting. The image shown here, and I'll come back to this a little bit later, but the image shown here, the skylights are actually, we have an equal amount of glazing. So the glass area on both of these images is the same. It's just the ceiling design is different, and you can see the brightness difference. So I'm going to come back to that concept a little bit later. So today's presentation is going to start with energy. It's where I started my career, and we're going to move on from there. I'm going to touch on durability, and both of these topics I will review a little bit of what's in the code and give you some understanding of that information, and then try to take it a couple of steps further to give you a little bit more background information on how to consider skylights in your design and how that could help you improve the experience of your design. And then, inspired by my work with Active House over the last few years, we're going to wrap it up with some discussion on comfort. So the first time I went through this presentation, when I was expanding it out for the 1 hour time slot, I started to feel like, wow, I'm talking a lot about the challenges of working with skylights in the Canadian climate, and with all these considerations, and perhaps I'm making it overly complicated sounding. So I wanted to start this section by saying that skylights are amazing. They can do a lot for a space, and with just a few tweaks and a little bit of deeper understanding on how the energy side works with skylights, you can include them in high performance buildings. And we are doing this with a number of projects and a number of architects doing high performance buildings, and we're getting a deeper and deeper experience both from our colleagues in Europe as well as the projects that we're doing locally here in Canada and North America. So let's get into it. Energy, I've broken into thermal efficiency and solar heat gain. Those two go really well together. And then I'm going to touch on air and water tightness, and then finish off this section with some comments about seasonal considerations. So the first thing we talk about when we talk about windows and energy is the U value. And most of us are more familiar with this R value, that the R value being the insulation value of a wall. A U value is actually the inverse. So a lower U value is better, and U value is also effective. So it means it's the frame and the glass are both included in this thermal efficiency number. That number is referenced in prescriptive code, both in Part 9 and non-Part 9 projects. And then we've got the solar heat gain coefficient. Most often comes up in non-Part 9 projects, but this is the amount of heat gain you have from the sun coming through the glass. So if you had no glass, if it was just an opening in the wall, the sun was shining through it, you would have 100% heat gain. But when you add glass and coatings and another layer of glass, you start to reduce that solar heat gain from that direct sun. And that's what we're going to talk about. And that's important, I'll say, for two reasons. One, Monica mentioned last week that we can get 2 to 3 times more light through a skylight than a vertical window. That also correlates that we can get more heat in the summertime through a skylight. So we need to keep that in mind, because high performance buildings really airtight, well-insulated buildings often are more susceptible to overheating. And this happens even in Denmark, where our head office is. So it's going to happen in Canada as well. So we have to be smart about how we're using windows and skylights in high performance building. So these, both of these performance factors do follow test standards. So when we're testing our products, we're working with North American test standards, and I've shown two, the CSA and the NFRCA, which is American but accepted in Canada. Those are the two that we work with. They're going to give you both of those performance factors. Now, if you're bringing products in from Europe, and we sometimes do bring products in from Europe, the U value that they have coming in from Europe is a little bit different. So U value has to do with the temperature difference between inside and outside. In Europe, they use a smaller difference in temperature. In other words, they use a warmer outdoor temperature than we do. So their U values often look better. If you took a skylight and tested it to the European standard and tested it to the North American standard, the European performance would look much better just because of the temperatures they're using. Now, the other element for skylights, this isn't the same for windows, but for skylights, in Europe, we test skylights vertically. In North America, we test skylights at a 20-degree angle. So that lower angle also increases your U value. So that makes it look worse than it would if it's European. So just a couple of things to keep in mind, as I know a lot of us, as we're looking at these high performance buildings, it's very tempting to look to Europe to bring product in. So just factor that in. These are the two main values that are mentioned in energy codes, both Part 9, if you're in Ontario, the SB12, or most of the rest of Canada, 9.36, you would have a maximum U value. Because lower is better, they set a maximum U value. And that would be based on your climate zone, so your geographical location within the province. When you start looking at the National Energy Building Code, then you're going to have both of these factors. So depending on your climate zone and the type of building you're doing, if you're going prescriptive path, they will give you a maximum number for each of these values. And if you're doing energy modeling, and most projects I understand, and the ones that I'm involved more intimately with, are doing energy modeling in order to optimize the cost and performance of that building. So most of your energy modeling platforms are also going to be using these values. And I like this approach better in part because it gives you more ability to encompass some of the tips I'm going to give you in order to improve the energy efficiency of the skylights in your projects. The other thing I like to bring into this is that if you're doing energy modeling, doing daylight modeling might not be that difficult to add on. And if you're really clever about it, you can do an iteration back and forth with your energy model and your daylight model in order to optimize both of them. And then you might start looking at things like the ceiling design from Monica's presentation last week and seeing, well, we want to get better daylight in here. What can we do but still not have too much of an impact on the energy? All right, so how do you get a better U value? So this piece of glass, this assembly of glass, us window guys will call it a IGU, which is a insulated glass unit. And what you're looking at is a triple pane IGU. And it's got the 3 panes of glass and then 2 spacer bars in between. So typically windows will be a double or triple pane. Triple pane will be more energy efficient. It's not the extra layer of glass that gives you more efficiency, it's the extra airspace between the panes that's giving you the efficiency. That's the insulative value. Now that airspace is often filled with argon or the more exotic krypton, which will give it a better thermal performance. So the U value is lower with that. We also look at doing low emissivity or low E coatings on different surfaces of the glass. And this reduces the heat that radiates through that pane of glass, which improves its thermal performance. Things like laminates and things like that, they can affect it a little bit. Spacer bars, they should be low conductance. So historically, we used aluminum. Aluminum is an extremely good conductor of heat. So aluminum is not a good spacer material. So you want a structurally strong spacer, but one that's also not going to conduct very much heat. And the thickness of that spacer changes a little bit. And you'll notice that a lot of products from Europe will have a larger airspace in between, and that's in part due to the testing temperature that they're using. So they often will have closer to 2 centimeters, 2.5 centimeters, where we might have a half to maybe 2/3 of that in our spacing, typically in North America. I covered everything there? Yes, let's move on. Now the second part that's included in the U value is the frame. Now the frame is super important because I'd say in North America and being involved in the fenestration side of things, we've been able to get better glass, coatings and better spacers. And the next big push, and this is happening more so in some parts of Canada than others, but the next big push is more energy efficient frames. So in this case, I'm showing a fiberglass frame because fiberglass is a very low conductance. It doesn't conduct a lot of heat. There is aluminum cladding on the outside, but it's not extending to the inside. If you're using a aluminum framed window, you'd want to make sure that window is thermally broken, which means the aluminum on the exterior has some non-conductive material connecting it to the aluminum on the interior of that window. And any window that's being sold in Canada should have that. The thermal diagram on the right, you'll notice that it's warm on the bottom. This is a cross section of a skylight, two skylights actually butting up against each other, so you can see the frame between them. And it's demonstrating that if you have a well insulated frame, that you should be able to keep that frame, the inside surface, warm. And if that surface is warm, that means you're not losing as much energy through that skylight in what would be a cold situation outside. So you want this cross section, this thermal image, to be as warm looking as possible because that'll be a warmer skylight. Now, how you integrate into the building is not count as part of the U value, but when you're looking holistically at the energy performance of a building, you have to factor this in. Now, on sloped roofs, you could integrate the skylight or inset the skylight slightly into the roof. And we do this to some extent with some of our residential products going on sloped roofs. But if you're doing commercial projects and you're going to be operating on a flat roof, you likely have to lift your skylights up off the roof to get them out of the snow and watershed situation at that location. So you're going to have what we call a curb. A curb is the structure that the skylights are going to sit on. So to have a high performance system, we should be looking at how do we insulate that curb to make it a better energy efficiency. Now the next one I alluded to a little bit when I had one of Monica's slides up, and this is a variant on another one of her slides. So in this case, we've got two equal skylights. The lower images are showing the daylight factor. And you'll see the image on the right is spreading the light out further. And there's not a big compromise in the brightness in the middle of that space, but the light is going out further. And that's simply by flaring the light shaft. Now, how does this factor in with energy? Well, if you could flare the light shaft and have better design at the ceiling level, you could actually reduce the size of the skylight a little bit and still get comparable amounts of daylight. So this type of approach is similar to what I was suggesting earlier with the daylight modeling and doing an iterative design with the energy modeling. You can do little things like this and you could reduce the size of the skylight, still get good daylighting, but reduce the energy loss in the wintertime through that skylight. So little tricks like this go a long way. Okay, moving on. Solar heat gain. So solar heat gain is really when direct sun is coming in. So I chose a couple of images where you can see that direct light coming into the space. That direct light is the radiation is coming through from the sun and it's going to heat the surfaces that it's landing on. And that is going to then radiate heat to the room around it. That's your solar heat gain. So I mentioned earlier, this is the category, the performance factor that is going to become more and more important. But even if you're working with just the solar heat gain, it's important to look at how else can you reduce the risk of that solar heat gain. That's what I'm going to talk about here. So the first thing I want to just introduce before I go to the first strategy to reduce solar heat gain is talking about the sun's path, orientation. I've literally been looking at these drawings, probably a little bit more detailed than this one, for almost 20 years now. And the real simple bit is that in the northern hemisphere, the sun comes up in the east, it crosses the southern sky, and it sets in the west. It's higher in the summer than it is in the winter. So the sun angles change depending on the time of the day, as the sun goes from east across the south to the west, and depending on the time of the year. And this is all predictable, though. We know that about December 21st is going to be the lowest sun angle. That's the winter solstice. We know that on March 21st-ish, plus or minus a day, and September 21st, those are your equinox times of the year, and that we know what the sun angle will be. And then on June 21st, on the summer solstice, we know those sun angles. So you can predict where the sun will be and design in accordance. So this is called a north light, and like the name suggests, you're facing the skylights towards the north. And the advantage of this with regards to solar heat gain is that you're not going to get very much direct sun. Only in the summertime in the early morning and early afternoon, you might get some low incident angle sun from the rising and setting sun. But for the most part, you're not getting a lot of solar heat gain here. So you're getting this nice even distribution of light in the space, and you don't have a lot of solar heat gain. And this is really common. This is a school project that you see here, but this is really common in warehousing in Europe, and is kind of a traditional way to do daylighting. You see it occasionally in North America, and I can say that we do have an exciting project coming up later this year where this is designed in. So I don't want to say any more about that, but it is still something that's being considered now for North America, and it's a great strategy for reducing solar heat gain. Interior blinds. Interior blinds are primarily used for glare, and I'm going to talk about glare later, but with regards to solar heat gain, they do reduce your solar heat gain by 30 or 40%, depending on the blind, depending on the application, or on the product, but they can reduce the solar heat gain. And they do that in part because the heat's already getting through the glass, but you're heating up the blind material. Some of that heat is radiating back through the glass, and some of that heat is radiating into the space below. So it's not optimal, but it does reduce it. What is optimal on the blind side of things is when you do exterior blinds. And this isn't a popular approach in North America. It is much more popular in Europe, and I think it's extremely clever because this approach could allow you to use high solar heat gain glass, so that in the heating season, which is most of the time, most of the year in Canada, you can benefit from the heat coming in through the glass. And then at the peak parts of the day in the summer where you don't want the solar heat gain, you could close these light transmitting semi-transparent blinds to cut down that heat gain. So it's a super clever way to approach solar heat gain and optimize energy over the year. This image, it's a bit small, but you can see it's three types of glass. The top one is clear. The second one is opal, which is actually a white laminate. And then the third one has a frit pattern on that, so that would be for birds. And the top one has a solar factor, so the G value is solar heat gain in North America. It goes from 59% with clear to 38% with the white laminate, and then down to 35% with the frit because they're blocking light. So that's another approach. You can do some treatments like tint and frit that can also reduce the solar heat gain. We'll talk a little bit more about what else to consider with that later on. That brings us to durability. So durability, we're really looking at structure, and that's mostly to do with the building code requirements that you're going to be working with your structural engineer. This varies based on the location. It can vary a little bit about with regards to local terrain and also with how the roof is designed. So both your structural engineer and your roofing consultant may be involved in this discussion. I know on our side, we often on bigger projects will go back and forth with the structural engineer to make sure that the skylight that we're proposing is going to meet the anticipated snow loads in that location. Air and water tightness, and then condensation, and then just quickly on fire. So the North American Fenestration Standard CSA is a contributor to the standard series. There's more than one of them, and it covers off structure. And for skylights, we're looking at design pressure. You're really looking at snow and wind loads. So your snow loads are going to be that downward force. It's a bit counterintuitive, but the downward force is positive in this application. And then you have your upward force, which is your wind. And we have to design for anticipated local conditions. And in some parts of Canada, you can get very high loads of snow. So we have to factor this in. If we're doing a project in Whistler, which according to my chart has the highest snow load of all the cities listed in Canada, you have to anticipate that you're going to have a lot of snow weight sitting on the skylights. Now the image on the right is a little bit different. This is two roofs. This is a snow drift that's developed due to the wall or the second wall construction leading up to the higher roof. We had a project in north of Montreal where we were looking at a skylight that was going to run right into that upper wall. And we had to play around with the design a little bit because they did anticipate drifting like you see in this image. Okay, so the Canadian supplement to NAFS does look at air and water tightness. Both of these are important, and I'll spend a brief moment on each of them to give you a better understanding of why. So this, when we do this presentation as an in-person, this would be a video. Video doesn't work so good on webinar, so I just took a still image. What you're seeing here is a spray deck. So this is over top of a test skylight. We also have this is in a wind chamber, so there is a large fan blowing air at 30 meters per second. So it's producing a pretty high wind while spraying water on it to simulate rain. And what you can't see in the image very well is there's actually a technician below the skylight with a flashlight who's inspecting for water ingress, so a leak through the skylight. And when you sell skylights, you definitely want to make sure that they don't leak. And with our residential line, we've even branded it the No Leak Skylight because we know that that's something that resonates with people. So moisture protection, especially with skylights, is an important consideration. Now, when is a leak not a leak? Well, it's not a leak when it's condensation. And condensation is a challenge, can be a challenge for skylights, particularly if they are low performing skylights or it's in a very high humidity application. Skylights by nature being sloped are more susceptible to condensation than vertical windows. So we got to keep that in mind. There's a couple of strategies to reduce that risk of condensation. So what all good building science presentations will have at least one psychometric chart in it. So I've included this because I'm talking about condensation. But very quickly, what this chart allows you to do is that if you have a room that's 21 degrees Celsius and 40% relative humidity, you can determine what surface temperature will cause condensation. So we take this over there, and then you're going to get condensation if you have a surface temperature that's 7 degrees Celsius or less. So at 40% humidity, if we took something out of the freezer or say had a cold glass of liquid with ice in it, you would have a chance of getting condensation if it was less than 7 degrees Celsius. So this is important for skylights because we want to make sure, if we think of that warm skylight frame, that the surface is going to be warmer than 7 degrees in this case. So in Denmark, they require you to have a heat source near skylights. And I see this in some applications here, not always. It's definitely a belt and suspender approach. And this heat source is going to help you keep the skylight warm. And this is important for two reasons. One, it will reduce your risk of condensation, and it'll also help with comfort. And I'll come back to that later on. the really real challenge for us at this stage, when skylights are getting so energy efficient, is that if you have the temperature and you can handle much colder temperatures and keep that inside surface above, say, 7 degrees as the example I showed, do you still need that heating source up by the windows? Because when we're thinking about energy, if you're applying heat up there, then a lot of that heat's just going to be lost out the window. If you have a really high performance building, the location of your heating source becomes less important. So you might not need it near the skylights when you're using really good performing skylights. Okay, so moving on, the stack effect. Let me define this for you. So the stack effect is simply hot air rising. Think hot air balloon. Within a building, when it's cold outside and it's warm in the building, the warm air in the building wants to push up towards the top of the building. And then if it has any ability to leak out of the building, it will pull colder air in through the lower building. And in a very tall building, you'll actually have an equilibrium at the point in the height of the building of where the positive pressure from at the top transitions to negative pressure at the lower part of the building. So why am I bringing this up? Well, we put skylights at the top of buildings. So when you have air that wants to leak from inside to outside, this is a concern. And I'll use this little example. The building code still refers to vapor barrier, and a lot of us in the industry still refer to the layer that we use for air tightness and for vapor to protect it from vapor diffusion. We still refer to it as the vapor barrier, but we should be calling it an air barrier, because the air tightness is so much more important, especially at the top of the building and especially with skylights. So this is a little example that I took from a friend of mine who's a building consultant. This comes from a building science study, a little experiment, I guess not experiment, just a study they did theoretically, where they compared the vapor diffusion, so how much moisture would diffuse through a sheet of drywall over a winter given the conditions. And they compared that to the amount of water that would be in a 1-inch hole in that wall. So same amount of time, 1-inch hole of air leakage versus a 4-foot by 8-foot sheet of drywall with vapor diffusion. So the drywall over a winter had 1/3 of a liter leak through. Get ready to be surprised, because the 1-inch hole had 30 liters of water leak through it. So not only is air tightness important for energy efficiency, it's also important for the durability of the building, because you don't want air leaking through your building envelope and depositing water through there, because that water hits, or when moist warm air hits a cooler surface, it can cause condensation. Condensation could build up to larger amounts of water and could cause damage in the building. When it comes to building durability, water is one of its biggest enemies. So you don't want that in your building assembly. And when we stick the skylights at the top. Now, this was the one thing that didn't work when we transferred the presentation into this platform, the Adobe platform. But the rule of thumb that I was going to demonstrate here is that you need to have a continuous air barrier. So when you draw an air barrier, you shouldn't take your pen off the paper. So in a cross section of the building, in this case a close-up of a skylight detail, you should not be taking your pen off of the building or off the paper when you draw that. So the skylight has to be properly integrated into your air barrier of the building. Okay, one slide on fire. This doesn't come up very often for me, so I don't have a great amount of detail. But we do, and many companies sell what I would call combustible skylights. And these are going to be your plastic dome or sheet skylights. The code does, and I apologize, I've referenced the Ontario building code, but it is the same. I just didn't have the numbers handy in the national building code, so I expect most of Canada will have a very similar version of this. We do flame spread testing. So this is a test that's going to give you a number, a maximum number that material passes. And I know with our products, our acrylic material is less than 150. Our polycarbonate material is less than 75. So we have products within both of those categories. And what that's going to dictate is the maximum size of an opening, the minimum spacing between your skylight openings, and the amount of ceiling area, the percentage of your ceiling which doesn't come up in any other scenario when we're working with skylights, on how much, there's roof area and there's things like this, or glazing to floor ratio. This is the only incident, or the only time it comes up where it's a percentage of the ceiling area. And with regards to sprinklers, the maximum rating might be tied into whether that space has a sprinkler or not. Sorry, just having a drink of water. All right, so moving on to part 3, and we're going to talk about comfort. So I'm going to touch on a couple of elements of daylight and visual experience, touch briefly on sound because it does come up with skylights, as well as thermal comfort, and then I'm going to end on fresh air and ventilation. Again, the VE in Velux is ventilation, so I've snuck that in at the end. First, I ask you, and this is almost a reminder to myself as well, we get so focused on energy. Code tells us we need to focus on energy, and this becomes a driving force in how we're designing buildings. And I know the RAIC and the Canadian Green Building Council are lobbying to have the code be more conscious of carbon, extremely important. But for the case of the next few slides, I'd like you to take your energy blinders off. So this is a reference to horse blinders and being able to focus, but if we can focus past or look beyond energy. Okay. Maybe I hit the button beside it by accident. So the first thing I want to touch on is taking a look at visual transmittance and the color rendering index. And there was a little bit of a foreshadowing of this when I had the slide up with the clear, the white laminate, and the frit design. But let me reveal these. So these are 4 renderings that are really looking at the color of the light and the color of the image on the wall. So this first one is no glass. This is as if we'd put no glass. This is just a clear opening above this room. It's a skylight application, no glass there. The second one is introducing just a double pane glass. It is a high solar heat gain glass, and you'll see our visual transmittance has dropped to 79%. So we've lost 21% of the light coming through that glass. And then we have our color rendering index. You can start to see, maybe you can notice, depending on the resolution of your screen, that the color on the photo or on the painting on the wall is a little bit more muted. We go to the next one, and we've reduced the visual transmittance, which reduces the solar heat gain coefficient, and we're getting an even lower color rendering index. And you can really start to see you're getting a more gray light. It's reducing the vibrance of the light, and so that's reducing the vibrance of the colors in the painting. And finally, a glass, it's basically a tinted glass. You can see that you're losing a lot of that light quality, a lot of that color quality. And this is in the name of reducing your solar heat gain. So when you're looking at tints and things like this, it's good to just keep it in mind that you are losing quite a bit of color and the quality of light. Now I'm showing interior photos, but this is the same when you look out of a building. So when you're inside a building looking out, your view is also going to be more gray. The colors that you see will be less vibrant when you're looking through a tinted glass. So that's one of the negative impacts of being focused on energy. And the big comment there, the big takeaway for me is that if you're able to, and energy is doing this anyway, if you're able to reduce the glazing, perhaps you can go with a clearer glazing in order to get a better quality of light and color coming through that and improve your view. It does put more onus on the designer to curate that view, place the windows where the view is going to be framing something nicely, but really that's good design anyways. The next item I'd like to touch on is glare. And glare is that discomfort you feel when something is brighter than what you're looking at. And that's something that all windows are at risk of, but skylight's getting 2 to 3 times more light. We are susceptible to causing issues with glare because of that. So guess what? A lot of the same things that we use to reduce solar heat gain can be reduced to, or be used to control glare. So exterior blinds, having coatings on the glass or facing skylights north. Um, the interior blinds, again, the interior blinds are primarily for controlling the amount of light. They help with the solar heat gain, but really it's for glare control. And then we have another system I haven't introduced yet, and that's the use of prismatic lenses. So this is a dome-style skylight, and there's a few manufacturers of products like this, and the inner dome is prismatic. So what it's producing is a very diffuse light, or 100% haze factor. Um, the image I chose on the left there, there's two skylights that have yet to be installed in that project, and you can see they're producing the hot spots on the floor, where the rest of the space is this nice even distribution of light. This is the type of skylight we would typically recommend for retail and warehouse applications. You're not going to get a view through this skylight. You won't have a venting fresh air option with this skylight, but you'll get a nice distribution of light in the space. Some of you, I recognize some names from last week. You might recognize this project from Monica's presentation. This is one of her favorite projects as an architect, and I'm going to talk about it from the glare side of things. So this project uses deep light wells, and those deep light wells prevent the direct light from getting all the way down to the floor area. Now it's using it's minimizing the horizontal ceiling surface, and it's got some lighting in there, but it produces an extremely even distribution of nice daylight in that space. And I'll give you an example a little closer to home. This is actually just a few kilometers from my house. I remember seeing it on the cover of Canadian Architect a couple years ago, and I gave the architect a call to see if I could use the project in my presentations, because this kitchen has that long light shaft. So this long light shaft is bringing light in, and the walls of that light shaft, the distance between the ceiling and the roof, they're flared all the way out to the vertical walls. So this is really neat. And if you look on the right-hand side, the top image, the actual photo of the project, it's showing this volume. And that volume is housing the light shaft. The cross section below, I apologize, it's a 90-degree rotation of the picture above, but that cross section image is showing how that light shaft is flared. So a great way to control glare and to produce a really even distribution of light in that space. Now, Monica last week talked about the strategies for designing with daylight, and next week Monica will be back again talking about designing for people and with daylight and fresh air. So I won't go into any more of the daylight parts because I'll be stepping on her toes. So I'll move on at this time to sound or acoustics. And there are really two scenarios that come up when we're supporting projects on this. The first is concern about rain. Now, I don't have my camera on, but I'm presenting from my attic right now, and I have two skylights over my bed, and I get woken up half a dozen times a year by the rain. So it is a concern. And then we get projects that are close to airports. And I lived in a test house a few years ago in Etobicoke, so not that far from Pearson Airport in Toronto. And I can say that airplanes are a concern. So how do we deal with that with skylights? Well, one of the ways to deal with it is very similar to how you would deal with thermal efficiency. So adding panes of glass, adding laminate to the glass are very good strategies to start with. Varying the pane thickness, so each individual pane being a different thickness also helps. And if you're a triple pane, you can vary the airspace depth, and all this will help reduce the sound transmission through the glass. Now, the last one is also good for energy efficiency, is make the skylight more airtight. Make sure the install is more airtight, and you'll have less sound transmission through that glass. Okay, so on thermal comfort, and I've blended in seasonal considerations with the thermal comfort here. On sunny summer days, we've already talked about solar heat gain. That's exactly what that's referring to. Because you want to be able to control or compensate for the heat gain you're going to get on those hot days. What we haven't talked about yet is clear winter nights. And it doesn't have to be at nighttime, but this effect that I'm going to talk about is most prominent during the nighttime and during the winter. So nocturnal cooling or radiative cooling is one of the concerns that one might have with skylights. And what happens is that on a clear night, outer space is very cold. Even with our atmosphere, it's still very cold up there. And this is the reason, it's this effect that can give us frost on an evening that is above 0 in temperature. So you could have frost on the ground, but it only got to 2 or 3 degrees in temperature. So this also has an effect with skylights. So with skylights, if your skylights are not very thermally efficient, by cooling them, you could increase your risk of condensation at night. So we talked already about that, but with regards to thermal comfort, it can actually produce, so if you're using low performance skylights, it can produce the sensation of a breeze, a cool breeze coming off those skylights. And what that is warm air goes up to the skylight, it cools, and then it drops back down. So you're actually feeling some cooler air dropping away from the skylights. That convective current is going to feel like a breeze. So this is another reason to have higher performing skylights, or as we saw in the image I showed with the Danish installation where they had the heater, providing some heat close to that skylight to reduce that sensation. But higher performance skylights reduce your risk of that happening. Okay, final topic. We're just about there. Fresh air and natural ventilation. So I introduced the stack effect earlier in terms of air movement within the building and how you get this upward pressure in the building. Well, we can use that to our advantage as well in buildings. We can use that for natural ventilation. So the stack effect is one of two different types of natural ventilations. The other one is cross ventilation, which would occur when you open windows on two sides of a building and you have a wind blowing. In this case, we're opening some vertical windows and opening up the skylights and allowing the skylights to pull air through the building. So by having operable skylights that open up, you can do night cooling. You can take advantage of night cooling with these, or you can take advantage of bringing fresh air into the space. We've seen an increase in interest the last few years of doing combination ventilation. So with smart buildings, you have the ability for the building to know, are the outside conditions good enough to open up the windows and bring some fresh air through? Or should we be using our mechanical ventilation at this time? So when we're working with these companies, we all are the HVAC designers that are doing these systems in support of the architects, we usually have to give one of two ventilation areas. There's different ways to calculate this, so we have these numbers available to provide to the mechanical designer so when they're doing the ventilation system. So the final thing I'll touch on is this project. This is an example of a project in the UK that's using this approach. This project has 200 skylights, half of which open along that center piece. So there is some PV on the near part of the building, but on the center part of that building, those are mostly skylights. And then you have the two office stacks on either side of that atrium. So within that atrium, this is what it looks like. They've got some structure there to reduce glare and give it some aesthetic appeal. But they are able on a nice day to open up those skylights, and people can open up their vertical windows in their office and allow the fresh air to flow through. Now, if any of you have been past the Velux Canada office in Oakville, it's just off the Queen Elizabeth Way. We have about 200 skylights in that building. Looks different than this building. But on a nice day, we will get an email and it'll say, we're not going to turn the air conditioning on today. Please open your skylights. So I think that's a really nice thing to have. I've got a number of venting skylights in my house. That's how I do most of my cooling. In the summertime, only when it gets high humidity do I even consider turning on the air conditioner. I can often drop the house temperature by 5 degrees Celsius by opening up the skylights overnight. And I think that's a good spot for me to stop, and I'll give Monica notification that I'd like her to talk a little bit about her presentation in just a minute. I'm going to wrap up with three conclusions. So, number one, a combination of high-performing skylights, accessories, and good placement are needed in order to optimize for both energy efficiency and I'll say for daylight for skylights, not just comfort, but daylight. Conclusion 2. Adding panes of glass, surface coatings, laminate layers, tints, frits, etc. can improve the U value or reduce the solar heat gain, but a penalty on brightness, color, and view quality should be considered in the design too. And my final one, skylights, like other building components, have to be selected, positioned, and integrated in an appropriate way for the local climate to ensure building durability and performance. And these are all things that we're happy to help you with early or mid or late in the design process. Happy to give some comment on that. So with that, I invite Monica to say a few words about next week, and I thank you for your time today.
Great, thanks, Russell. That was a great presentation. So next week is going to be designing for people with daylight and fresh air. So the first presentation that I did was kind of a big focus on the design of the architecture itself. But this time we're going to focus on the benefits of daylight and fresh air. And it's going to be quite case study heavy. So I'm going to be going through different projects that relate to residential, commercial. So there's going to be a really good mix of different kinds of projects and walking through them, understanding the concept of the project that the architect was going for, and how they use daylight and fresh air in design. So hopefully next week will also cater to be a really inspirational presentation and also give you some precedents of how you can be designing with daylight and fresh air in your upcoming projects as well.
All right, I put Monica and I's contact information there, as well as the link to the RAIC Corporate Affiliate Series, where you can register for the next 2 webinars if you wish to. And the link is in blue. I probably clicked on it already, but the Velux Architect Learning Hub. So we do have a landing page on our website where you can connect with us on skylights and designing with skylights, and connect with Monica and I if you'd like to review one of your projects. So I do see some questions coming in from Keith. Are most commercial Velux skylights constructed of fiberglass? We have one product line that is constructed of pultruded fiberglass. That is the Velux Modular Skylight, or VMS. It's what Monica and I spend most of our time supporting these days, and we bring that product in from Denmark. It's a product that was designed with Foster and Partners. It was featured in many of the images that I've included in the presentation. Other skylights, like our dome-style skylight, does have an aluminum frame with a gasketing system, so it's not fiberglass. So we have a comment. We older architects remember when talking about triple panes were laughed at. How common is it now? It's not overly common yet. We feel like it's the present, it's the now. But I attended a webinar yesterday with Fenestration Canada, and it was given from British Columbia, who is the area where I'd say is leading the charge with the step code, and they still only have a handful of manufacturers that are predominantly doing triple pane. Many manufacturers on the webinar yesterday are not offering that, and I'd say even at Velux, we're still in a transition phase. In the commercial side, we're seeing more and more interest. Our commercial product line, we have a smaller price increase to go triple pane, so that might be part of it. But I think there's more commercial projects doing performance modeling, so they have a better understanding of the energy benefits of triple pane. Where we see in residential, because we're still able to do Energy Star and meet building code with a double pane, predominantly in residential, we still see a double pane product. But there's a lot happening in the next decade a lot of change is on the horizon. So I think we'll see the big shift when building code moves to a position to require it. So I see somebody else is typing a question. And the glass broke at extreme cold temperatures. Have you corrected this? If you did a triple pane wood product from years ago, that would be a roof window from Europe. And we've done a lot of changes to those products over the years. It would depend on the model. One of the groups, in my role, I work predominantly in commercial business development with Monica, but I also have the service team on my under my command, and so we get to look at these projects when we have issues. Um, so it depends. We don't hear about cracked glass very often, but if it was tempered or float glass, sometimes there's minor flaws in the glass which might not be present in normal temperatures but might present themselves in cold temperatures. My hope is that you're able to reach out to Velux and get some support from that, because I know certainly when those little things happen, my team is quite generous in helping out. So there's a question about blinds on the exterior rather than the interior. So with regards to light control, so if you're just looking at glare, then the exterior and interior blinds are gonna have a very similar effect. If you're working with blinds for the purpose of reducing solar heat gain, then the exterior blinds, when the sun hits the blind, it's heating the blind up, but it's still on the outside of the glass. So not as much heat with an exterior blind is entering into the building. When you have a blind on the interior of the skylight, that heat is going through the glass, heating up the blind surface, and a lot of that heat is radiating down into the building, but some of it is radiating back through the window. So for heat control, for solar heat control, exterior blinds are more effective. What about snow conditions? Great question. When it comes to snow, and that's I should have been more explicit about that, because of course this is a concern in Canada. And I remember the intermodal building before they joined another engineering firm had some exterior blinds on it, and chatting extensively with them about it. And the blinds, exterior blinds are predominantly for the hot season. So they're really exterior blinds. If you're using them for heat control, you need that heat control in the summertime. So in the wintertime, when you have a risk of snow, those blinds could be kept closed or kept open, I guess, in a rolled up situation. And if they're rolled up, then they're not going to be, you're not operating them with any snow or ice on the skylights. And the sun angle being lower in the winter, you have less chance of glare through a skylight in the wintertime than you say you would a west-facing window in the afternoon. So that's a consideration. I really think that the exterior blinds are going to become more interesting in the North American market, particularly in Canada, because if we can take a more holistic look at our windows, the way they do in Europe, and they don't have the extreme climate that we do in Canada and Europe. But the conversation there is really about energy balance. We know we're going to gain a little bit more heat, or possibly gain a little bit more heat in the summertime than we'd like to. So how do we handle that? But we'd like to gain a little bit more heat in the wintertime. How do we take advantage of that? So they're a little bit more holistically thinking. So a lot of the inspiration for the topics I talk about come from Europe. They're not coming from our North American experience. So Errol, who asked the snow question, was just saying thanks. I don't see anybody else typing anything in. I'm not in a hurry. We can take a few minutes if there are any other questions. Our contact information, I see a bunch of our links on this image are in blue, but I do have the email and direct telephone numbers for Monica and I on there. So if any of you had any other questions later on, you're welcome to reach out to me by email or telephone and we can chat. As you picked up from the presentation, I'm pretty interested in this. I've got a good level of knowledge on it, and interested. I'll say this: if you can challenge me with a question I don't have the answer for, and this does happen on occasion, I know a lot of people that know a lot more than I do that I can reach out to and get some help getting an answer for your question. So if we don't have any more questions, I will say thank you for everyone who joined us today and invite you to join us the next 2 Fridays. We've got a presentation on the benefits to people next week by Monica, and then Monica and I will be presenting together on the May 22nd on actual product. We'll be taking a quick tour of residential product and application as well as commercial product and application. So I wish everybody a beautiful Mother's Day weekend. If we have any mothers on the webinar, happy Mother's Day. And I'll stop talking. I'll watch this, see if any more questions come up, but I'll stop talking.